Okay, last lecture we stopped with Lewis structures and talking about resonance structures. If you remember resonance structures, all that means is that when there's a double bond in a structure, that double bond will switch positions constantly around, between the different elements. And when we talk about this in terms of formal charges, which is what we're delving into right now, formal charge, we call it kind of a bookkeeping system. And all it lets us do is try to determine which will be the most stable, best contributing resonance structure. So out of all the resonance structures that are possible, which one's going to give us the best, most stable compound? We're going to call that the one that contributes the most or the best contributor. So in order to calculate formal charge, we're going to do it for each and every element within the compound. And it's simply, if we're looking at one element in a compound, we're going to take the number of valence electrons that element has. We're going to subtract from it the number of non-bonding electrons or electron pairs, lone electrons, and half of the bonding electrons. So a couple of things about resonance structures. They must all have the same connectivity. So a resonance structure is not something where you will change the connectivity. Okay, so for example, if I had this, just as an example, a resonance structure would not be that. That's not a resonance structure because the connectivity is different. Here, the carbon is bonded to the nitrogen, which is bonded to the oxygen. Here, the nitrogen and oxygen have flip-flopped. So we can't change positions of where these elements are. They must have all the same number of electrons for each resonance structure. Second row elements have a maximum of 8 electrons, and this can be bonding or non-bonding. Third row elements can have what we call an expanded octet, meaning more than 8 electrons surrounding the central atom. Formal charges, the totals for all resonance structures must be the same. The best structures have fewer formal charges. Best structures have smaller formal charges. And the best structures will have the negative formal charge on the most electronegative atom. So let's look at an example. If I just look at HF here, and I want to calculate the formal charge on the fluorine, I'm only looking at the fluorine. I'm going to take the total number of valence electrons fluorine has, which is 7. I'm going to subtract from it the number of non-bonding electrons, so 2, 4, 6, plus half of the bonding electrons. So there's 2 bonding right there, so half of 2 is 1. So doing this math, I can say 7 minus 7 equals 0. So the formal charge on that fluorine is 0. You can see they've done the same for hydrogen here. Hydrogen has 1 valence electron. There are no lone pairs or non-bonding electrons. And there's 2 electrons shared between the hydrogen and the fluorine. So 1/2 of 2. 1 minus 1 is 0. So both formal charges for each element is 0, which is great. Very, very stable. Okay. Now, if I were to consider the formal charges of each element here, because remember, this is going to have resonance. So the other resonance structure could be this. Okay, that could be the other resonance structure. So This oxygen right here, the one on the left, it has a total of 6 valence electrons. There are 4 non-bonding electrons or lone pairs, and 4 bonding. So half of that. So that should be like this. I don't know why it's doing that. Okay, mathematically it'll work out the same. I just prefer to stick with one method. So we get 6, 4, and half of 4 is 2, minus 6, 0. And that's awesome. The right oxygen, it's going to be minus 1. It's a higher charge, but at least it's the negative. And the negative we want on the most electronegative thing. If we have to have a negative, we want it on the most electronegative thing. And then sulfur, if you do the math, it's plus 1. Now, if we look at this example here, and we say, okay, which is going to be the better structure or the favored structure? These are not resonance because the connectivity is different. But if we were going to do a reaction, there is a reaction where we take structure A and convert it to structure B. The question is, which is going to be more stable? Okay, so if we go ahead and do the math for each element, so this is hydrogen, carbon, nitrogen, okay? What we will find is that in structure A, they all have a formal charge of 0. In structure B, again, hydrogen, nitrogen, carbon, a 0, a plus 1, and a minus 1. Structure B has higher formal charges on each individual element, which is less favorable than having 0. So structure A is going to be the most favored format of that compound. So this will look like what you'll be asked. If I give you 3 different resonance structures, or if I give you 3 different resonance forms, what is going to be the best contributor? Okay, the most stable. So when you look at these, you're going to have to figure out the formal charge on each and every individual element in each structure. So if you look at structure A, B, and C, okay, and we do the math for each one, oxygen has 2, 4, 6 non-bonding. It has 6 valence electrons, and it's got 2 shared, so half of 2 is 1. That's where the 1 is coming from. So 6 minus 1, minus 1. So that formal charge is minus 1. Carbon has 4 valence electrons. There are no non-bonding or lone pair electrons, so 0. And it's got 2, 4, 6, 8 bonding. 8 divided by 2 is 4. So 4 minus 4, 0. And then nitrogen the same. It is also going to be 0. Okay? Now, if I look at B, we can see 2, 4 non-bonding, 2, 4 bonding, half of 4 is 2, so 2. So 6 minus 6 is 0. That's good. We always like oxygen to either have a 0 or the negative formal charge. Carbon, 4, 0, 4, so it's still 0. And nitrogen, 4, 2, net is minus 1. Now if I look here, oxygen is going to be plus 1, carbon is still going to be 0, and nitrogen is going to be minus 2. We can automatically eliminate that one. And the reason we can automatically eliminate it is because the most electronegative thing in that compound is oxygen, and it's carrying a positive formal charge. Oxygen does not want that. It can't handle it. It doesn't like it. It's not going to happen. Okay? A and B, they have the same amount of formal charge. Both have a total of -1 and -1. So that's not bad. It's at least negative. But in structure A, that negative is being carried by the most electronegative thing. Therefore, A is favored over B. And A and B are both favored over C. Could B occur? Yes. Will it occur? Probably. Is it going to be, if I had a racemic mixture or a mixture of both compounds, that's what a racemic mixture is, compound A and B in the same flask, if you will, or the same beaker, we're going to see about a 70-30 split of 70% would be A and about 30% would be B. I recommend going through the next example on your own and making sure you can do this. Okay, now I already talked about expanded octets. So there are some exceptions to the octet rule. Expanded octets and incomplete octets are two examples. We already talked about an incomplete octet in the last lecture when we talked about BF3 and boron being an exception. It does not need an octet. Some other ones were hydrogen, lithium, okay, those smaller compounds. They don't need an octet. They don't want an octet. They have no place to put an octet. Boron could put an octet in there, but it doesn't want it. Okay, so some exceptions to the expanded octet or the odd electron, which we refer to as a radical. Odd electron just means a single electron that's not paired, aka a radical. So odd electron species or free radicals or radicals. These are either, you're going to see it most frequently in compounds that are overall charged. So there, instead of a lone pair of electrons on it, there will just be a singleton electron, and that is referred to as a radical. Okay. Other odd electron species could be an incomplete octet. All right. Now, legitimate, this is an important part right here. Lost my pen. Legitimate Lewis structures cannot be written for they do not meet the octet rules required by the Lewis model. So just because we can do an expanded octet doesn't necessarily mean it's following Lewis. We still kind of write it out the same way, but different parameters are involved. So if we look at an example of odd electron species, one of them is nitrogen monoxide. There's only 11 valence electrons total. There's no overall charge on it. And so distribution of the 11 electrons cannot meet the criteria under Lewis. So that's one of the problems with the Lewis structure theory. And so what that means is the Lewis structure model, it won't work for every single compound out there. Nitrogen monoxide does exist. It is an actual, no kidding, molecule, but it doesn't follow Lewis's structure. So incomplete octets just means something does not have 8. We talked about that. BF3 and BH3, those are going to be your most common. Expanded octets means that there's more than 8 electrons on the central atom. And typically we see that with third period nonmetals and down. So like from the third period, which is the across, and down with those nonmetals. They will follow the octet rule if they're not the central atom. If they are the central atom, they can have an expanded octet. So a good example is XeF2. So if we're going to draw the Lewis structure for this, Xe is our least electronegative. It's going to be surrounded by fluorines. Xe has a total of, where's my periodic table? A total of 8 valence electrons. We know that because it's in row 18, right here, So row 18 has 8 valence electrons, and there is one of them. Fluorine is in group 17, so it's got 7 valence electrons, and there are 2 of them. So that leaves us with 22 total valence electrons available to us. Divide it in 2, we get 11 pair. Okay? All right, now we're going to do what we did each time. Fluorine is going to get first dibs on all the electrons. So 1 pair, 2 pair, 3 pair, 4 pair, 5, 6, 7, 8. All the rest go on the central atom. 9, 10, 11. Okay, so xenon has 2, 4, 6, 8, 10 electrons surrounding the central atom. This is an expanded octet. It is more than 8. Okay, this is going to stop part 2. Part 3 should be up shortly.